So good morning. So this is MECHENG 3A. So this is week 2 of the lecture, and it's a Tuesday. So the agenda for today is we are going to look into unsymmetric bending. I'll do a very quick recap on where we were before, and then we are going to look into how to identify second moment of area. Students usually, not all of you, but usually get confused on which second moment of area to take. Today, I'm going to help you. I'm going to help you identify easily without memorizing anything. Only a few things that you have to remember, okay? And then we are going to go into eccentric symmetric bending. So if I were to recap last week, we have a structure, okay? So we have a structure that's loaded with evenly distributed load and a point load, as you can see. So this is last week's lecture. Then I've drawn different cross-sectional area, cross-sectional area 1, 2, and 3. And now we know why all of them are known as symmetrical bending. This is because stress A or stress alpha will be equal to stress beta for all the cross-section, and stress at I is equal as J in all cross-section. Okay, why is that? Because it is all depend on symmetric loading. It's all depend on the distance y1 and y2 only. Okay, that's why in alpha and beta, the formula or they share the common y1. So the y you just plug into here, you calculate your stress, and I and J likewise, Y2 is the same for I and J. So if I were to recap into the introduction where we were, okay, so in the introduction which I was teaching, so what we are trying to do now down here is we are trying to find the stresses at point A induced by the moment that is 25 kilonewton and 100 kilonewton from an example. So that's why you see moment about X, moment about Y. So now we are going to look at, for today, we're going to look at unsymmetric bending. Okay, so unsymmetric bending, I'm going to draw for you in a situation where you will have unsymmetric bending. So starting from, before I go on, any questions so far? Okay, no. All right, so we're going to look at unsymmetrical bending. Right, so I'm going to draw a case where this diagram over here is unsymmetrical bending. So we have, again, we have a structure that is a rectangular. Okay, so this is our structure. And then I'm going to incorporate our transformation. So this is our transformation. So 1 is our Y, and over here is our Z. Then we have a moment now. So how the moment is applied? The moment is no more parallel to the x-axis, or sorry, y-axis or z. Now the moment has component of y and z now. Okay, so this is our moment. Okay, this is our moment M. And based on right-hand rule, if your thumb point towards the arrow, your right-hand rule, the rotation of the moment, it goes this way. Okay, that's the moment. So for this moment that has two components, we are going to break them down into my and mz. So this is your mz. Okay, so this is over here is your MZ. And you have another one. This will be your MY. Okay. So this is your MY. So I'm going to transfer MY. Okay, I'm going to copy MY and put it on over here. Okay. So this is your MY. And let's look at how we break them to component. So we know that this angle, given this angle over here, this angle over here will be theta. Okay. The angle over there will be theta. So we will break them down to components. We have MY is equal to M sine theta. And MZ will be equal to M cos theta. Okay. So for this case, this style of loading is what we call eccentric or centric, unsymmetrical, bending. Okay. Where the formula now has evolved. So we are still calculating stresses. So if I were to draw our transformation now, a smaller transformation. So we know that this is our X, sorry, our Y, our Z coming towards us is our X, and this is our rotation in the X-axis. So in centric unsymmetric bending, so we are calculating the stress in the X direction, and this will be equal to My over Iyy multiplied by Z minus by Mz over Izz multiplied by Y. Okay. So I'm going to teach you how to remember this formula. Always look at the point where you have moment in Y. The second moment of area, you take about Y-axis. Okay. And then when you have moment in Z, the second moment of area corresponds to Izz. So a good practice when you see IMY, you know you put a bracket. Okay, this is going to be the second moment is IY, and MZ. This is going to be this is going to be taken through the second moment of area about the ZZ axis. So that's what I normally do. You make less mistake. Now, why this is minus? Okay, is because the z-axis over here is pointing towards the what? Towards the left-hand side. So that is why in vector form it's minus. Now, you know what? I don't want you all to remember whether plus or minus. I want you all to visualize, okay? I prefer you all to visualize and know, oh, this is always minus. You can forget. I know your test will be online. Maybe in the exam time, you look at formula and you start to panic. You got it the wrong direction. Okay, I will teach you how to like get this right without remember whether is it plus or minus. All you need to do is remember what I've taught you in the last lecture. Okay, so what I taught you in the last lecture, if we go back to the last lecture, right? If we go back to the last lecture, I need to go back further. Is it further? Right? If you look at this arrow now, okay, if you look at this green arrow that I've shaded, right? The head of the bending moment arrow is always going to be compression. The tail is always going to be what? Tensile. So we are going to do the same down here also, okay? So you use your right hand rule now. Okay, use your right hand rule. Let's look at MZ now. Let's focus on MZ. So right hand rule, MZ, when you grip the arrow, you will grip it this way, right? You use your right hand, you hold on to it, you grip it that way. So when that's the case, you realize that the tail end, due to mz, the tail end will be tensile, and the head end above the z-axis, okay, so mz will be what? Compression. Exactly like what I've taught you before. Okay, nothing changed. What I've taught you earlier last week, you can apply to the entire chapter of the book, and it will still work. Okay. So the next thing that we are going to look at is we're going to look at the green one, the moment about y. So I'm going to change to pink. Right. Again, you use your right hand rule. You grip. Right. So you know over here. Oh, it's going to be a mess. It's going to be my. I'm going to draw it slightly lower. Right? So you have over here. So you know on the right hand side, on the head side, my will be compression. And on the tail side of the bending moment, vector arrow, my will be under tensile. So this is what I mean by visualization. You don't need to bother whether plus or minus. I don't want you to worry about that. I want you to visualize it this way. Then is easier for you. Okay, or if not, it gets really confusing. Is it plus or minus? Okay, and then yeah, you get into trouble. So now, before I go on, I'd like to prove to you why. Okay, why this structure is under unsymmetrical bending. Okay, I'd like to prove to you why. Before I go on, any questions so far?
Eugene, in the diagram, it says MZ compression on in orange there. Should that be MY up there? Or
It's
I'm a little
correct.
confused by that.
The orange, okay, the orange, the M. So this is MZ, right? So the tail end of the arrow MZ is tensile. The head end MZ is compression.
Oh, so you're
Looking
just marking like the sides of it, not necessarily like the structure?
so this is relative to the neutral axis or the z-axis. Okay, it's relative to the z-axis. It's relative to this z-axis over here. So above the z-axis, mz is compression. Below the z-axis, mz is tensile.
Oh, I see. Okay, thank
Okay,
you.
so likewise for my, on the right hand side, my is compression because it's the head of the arrow, right? It's the head of the arrow, and then the tail end of the arrow is in tensile.
Got it. Thank you.
Okay, so is everyone clear about this? Anyone else? Any question? No? Okay. Right, I have so much in my mind now to tell you. Unbelievable. Right. So why is the structure under unsymmetrical bending? Okay. So if I were to copy the structure again, I will copy this. Right. Then based on vector, so we know that we do have a mz. Okay, so we know that we have our mz. I have a question from a student initial AN. Should the compression be my? Both compression and tensile are marked as mz. Is that true? I think
she actually spoke already.
Hey?
She asked that question. Speaking.
Oh, okay. You are good. Okay, you are good. Okay, because now I have two computers, I'm looking at your messages and teaching at the same time. Okay, so if you are good, tell me you are good or not. I have obsessive compulsive disorder. And yeah, that's my problem. Okay, so we have oh, it's in orange, sorry. So we have our MZ over here.